So I'm very pleased to introduce Taavi. When Taavi's not busily co-organizing PyCon Canadas, he is a defect poacher and futurist at FreshBooks, and he's going to talk to you today about log analysis with Pandas.
Hello. So, log analysis with Pandas. I work at FreshBooks. We do cloud accounting, formerly online invoicing. Really, it's the same thing, but different name. And so we do a lot of web stuff. So the kind of log analysis is web server log analysis. In doing invoicing, people put in clients, create invoices, ship those invoices off. So the kinds of things that we have web requests for are things like give me invoices. And we'll have some examples of that. I've got some actual server logs in here. Fernando mentioned that I should really say, if I'm going to talk about Pandas, that I should mention that Wes McKinney has this book out, Python for Data Analysis, because he's the guy who did Pandas. And it's a really nice book, so you might want to go read it. So, log analysis with Pandas. Pandas, in case you didn't know, is an open source BSD licensed library providing high performance, easy to use data structures and data analysis tools for the Python programming language, straight from the website. Installing it is not the most trivial thing, but it's not that bad. You do need you don't need ZeroMQ for that. You need ZeroMQ for the notebook. The iPython notebook is an awesome tool for interactively working on your code, trying to figure out. Oh, yes, big thank you to Fernando. Yes, for iPython. And the notebook is really nice. You can have these notebooks. They get saved in JSON format. You can share them with your friends. And it's neat to be able to go back and see what were you doing. As you can see, I'm doing slides in it. You can interleave code and text, markdown, all of that. It's wonderful. So you need ZeroMQ for that. Free type, I think, was to get matplotlib installed. And if you want HDF5 support, you'll also want to install HDF5. Which is horrible to install in CentOS 5.5, but not so bad on a Mac. Debian and Ubuntu, there are a few more packages. You might need the C compiler. And then the list of Python packages. iPython will then use PyZMQ and Tornado to get the notebook running. And then you'll need NumPy and matplotlib and Pandas to do the same kinds of things I'm doing here. If you want HDF5 support, you'll also need Cython and NumExpr and tables. To run it up, you just go iPython notebook, pylab inline. Pylab says, please import the MATLAB-like functions for just, say, plot. And it imports all of those things into your built-ins. And inline, because we don't want it popping up extra windows. It can be as simple as hello world. And you can go in here and say, hello world, PyCon CA. And you can just evaluate it, and it will dump out whatever you had returned there. And you can do fun things like inline plotting. You've got a bunch of data points from -100 to 99, plot this thing, and you get these nice little graphs in line. So it's a neat way to explore your data easily. And you can see that matplotlib even lets you use LaTeX syntax to get little mathematical equations in. You can also very easily do things like draw me a histogram. Here's a Gaussian distribution of 1,000 elements. Just make me a picture of it, and it just does it like magic. So, I did a previous version of this log server analysis using almost pure Python for everything and didn't even touch Pandas. And then at the very end, did this big chunk on Pandas, and people didn't quite get it. So I'm going to do a crash course in Pandas and NumPy, sort of how do they think, how do they work? Because that's where really a lot of the power of using Pandas comes from, is the underlying NumPy-like abstractions. So we have a series, which is a one-dimensional array. You can give it a list, 1, 2, 3, and you'll get an array. Has 1, 2, 3 in it. Each of these lists are homogeneously typed. So this is an int64 typed list. If you give it a float, then all of the items will become a float. And you can see the d type is a float 64. And of course, this is Python. Everything boils down to being an object. So if you stick everything in, OK, you've got everything. But they're objects. One of the more powerful things you get with NumPy and Pandas is the concept of broadcasting. So you can do an operation that would normally only apply to a single scalar element, but you can do it to an array or a list, and that operation will then be applied to each of them, and you'll get back something that's the same shape. So given that series that we had, containing 1, 2, 3, we can say a greater than 1. And instead of just saying yes or no, it'll return another series that has the answer to, was 1 greater than 1? False. Was 2 greater than 1? True. Was 3 greater than 1? True. And you can do this with the standard comparison operations like equals or greater than. So that's kind of neat. You get this broadcasting-like behavior. And you can also, of course, broadcast your own arbitrary functions, like you can pass in a lambda, say, I'd like all the even values to return true. So that's cool. With Pandas, you also get the concept of data frames, which I found out are like NumPy structured arrays. And
modeled after R.
Modeled after R, yeah.
Basically structured arrays, but with the R semantics on top.
Yes, structured arrays, but with R semantics on top. And so you get this data frame, and you can give it your list of lists for all your data types, and it's sort of like a relational, or not a relational, a SQL table where you get columns of consistent data types and many rows with that set of data types. And here we can also specify column titles. We can say, I'd like this column to be called integers, this one is called floats, this one's called objects, and here's my index row. So you don't even, you can give it keys. If you don't give it that, then it'll come up with its own synthetic ones. So we have this fun little data frame, and we can see that, in fact, it has data types for each of these. The integers is int64, floats are floats, objects are objects. So for selecting data, there are a whole bunch of magical things that you can do by doing getItem access. If you ask for floats, if you just do a single thing like that, you'll be doing column lookups. So it's very easy to have this data frame and just say, I'd like a list of all of this kind of value. We can get the floats. You can look up multiple columns at the same time. You'll get back a data frame that has only the things that you were actually interested in, like integers and objects. Doing slices, you'll end up getting ordinal rows. So note this doesn't use the index value. The index values don't actually have to be integers at all. They could be date times, as we'll get into later. So if we say D slicing from 2 onwards, we get indexes 3 and 4, because that was 2 and beyond in Python slice syntax. You can avoid a lot of the magic by just using the XS method. You can say, I'd like value 3 on axis 0. Axis 0 would be picking out rows. So this is the named 3 row, which had integer 7, float 8, object 9. And you can, for consistency, also use it on axis number 1. You can just pick out the floats. So you don't have to use the magic stuff if it's getting in the way. You can also, interestingly enough, do row access. So for columns, we could pass in a list of column titles and we'd get back those columns. We can do a similar thing with rows by passing in a list of Boolean values. So if we have a mask, true, false, we'll return the first and the third items, first and third rows from the list. Well, that's kind of a neat thing you can compose. Because if you can combine that with broadcasting, now you can broadcast a question across a column. You can say, you know, where the integers are greater than 4, and you can use that mask as a getItem value, and now you can select just the values you want. So it's kind of like a where clause that you've just constructed in pure Python. You can use things like NumPy's invert function, which will invert the Boolean sense of all of the things to get the other side of things. So you get a lot of nice functional composition. If you do need to talk about the actual index values that you have, they have a special column name. You can just go .index, and you'll get a series that is that index. If the words and the code don't really do it for you, I know sometimes I really like a picture of what's going on. So I sort of draw this up. This is sort of a data frame and a mask, and anytime you get a truthy value, it passes through. It's like a filter operation, and anytime it's falsy, that value doesn't go through. So normally, when we have a web application, we have logs. We have big, ugly logs. And I don't have time to talk about the logs and how you get them into a usable format. Usually there are horrible programs involving nasty regular expressions. You might consider logging in JSON. That makes the parsing a heck of a lot easier. So let's assume that we've got our logs into a CSV format. So I've got a fake bit of CSV file here. And we'll just assume that we've got a POSIX timestamp that says when this event happened, how long the request took, how many kernel ticks were in system and in user, how many SQL queries it took, how long the queries took in aggregate, number of rows returned in the result, all of that stuff. And we can use Pandas and say, read CSV. And you can give it the log file. You can say, hey, the first column is an index column. It's also a date column. So interpret them specially. And because it doesn't understand these POSIX timestamps, we have to add a little helper function that says, hey, you know, convert this POSIX timestamp into a Python date time. And that's a thing that Pandas understands very nicely. You'll notice I'm doing some GC stuff. When you're loading 1.8 million rows out of a CSV file, the garbage collector actually gets in the way. This is one of the few places where the Python garbage collector really hurts you, is when you're trying to load up bulk amounts of data. Because it will try to find circular garbage every 700 net allocations. And we know that we're just going to generate a huge amount of objects, and they're not going to be circular, and we're not going to throw them away either. So it actually drops the load time from 55 seconds to 35 seconds on my data set just by disabling GC. And it doesn't change memory usage at all. So that's the thing to keep in mind when you're doing bulk loads of data in pure Python. And if we say, hey, what's in that data frame, we get this really nice data frame. Once you've gotten it loaded up from CSV, you might not want to have to sit there for a minute and load it every time. So we can actually use HDF5. If you've gotten those bits installed, Pandas has a really nice interface to HDF5. You say HDF store, give it a file name. I learned yesterday from Scopaz that you can use compression, and that drastically reduces the amount of I/O that needs to be done. Usually I/O is a lot slower than the decompression that would have to happen. And with the compression library like BLOSK, it's really designed for loading and saving NumPy-like arrays. And so it's very CPU efficient and compresses the data enough that the I/O becomes a much smaller issue. And then you can just assign to the store dictionary style and get stuff back. So it's just a really handy way to say, hey, I've got this giant data frame, just put it on disk. I want to get it back later really quickly. So actually doing log server analysis. Let's say we load up some subset of the data from May 7th, from some internal FreshBooks stuff. And we can define a bunch of timing bins. Let's say we want to graph a histogram of the response times. And so we have response times from 2 to the minus 10 up to 2 to the 9. That's a really nice log range. And we can just say, hey, set the x scale to log so that it actually shows up nicely. The x label is the response time. The y label is the number of requests that took that long. And we can just say, give me a histogram of the elapsed with those bins. And boom, we have a nice little picture. And as was seen earlier, you can do interesting things with slicing and selecting your data in pure Python, and then you can just say, hey, give me a histogram of this subset of the data. Give me a histogram of just the invoices, or just the estimates, things like that. We can also do things like scatter plots, which help us to introspect a little bit more on correlations between different aspects of our response times. So if we load up the data from May 7th and May 8th, we can say, plot the May 7th elapsed time versus the May 8th elapsed number of rows returned to see, is there a correlation between how big a result set is and how long a request takes to service. And we can see that, yeah, there's this little bit of a line going up, but it's kind of a big blob. This was all the requests throughout the day for everything. So that's a little generic. And I happen to know that on May 8th, we deployed some code that was supposed to make the return result from invoice requests a little bit faster. And a little bit faster in an incremental way. It was supposed to make each invoice that we return just a little bit faster. So if you ask for 10,000 of them, it should make that a lot faster. So we do software releases at 9 a.m. So we take 2012 May 7th at 9 a.m. And localize it for the Toronto time zone, and then convert it to UTC and make it naive, because Pandas is only dealing with these naive UTC date times. And we do May 8th at 9 a.m. And then we can say, hey, give me all of the May 7th data where the May 7th index is greater than or equal to May 7th at 9 a.m. And now we have this nice subset of data. As I said, we only did the invoice things. We don't care about any of the other requests. So we can say, hey, where the May 7th after 9 a.m. Silo column says, hey, this was an invoice resource request. And then we get just May 7th invoice requests after 9 a.m. Well, that's kind of cool. And we can see if we just evaluate it that Pandas and iPython will give us this nice little summary and say, hey, instead of 1.8 million records, we only have 284,000. And they run from 1300 to 03:59:59 in UTC, which is 9 a.m. to midnight in Toronto. We've got 2 float types, 10 int types, and 2 object types. Cool. We'll do the same kind of data slicing on May 8th. So now we're comparing after 9 a.m. on the 7th to after 9 a.m. on the 8th. I know for a fact that our load looks very different throughout the day. And so we want to try to compare the same chunk of data from day to day. You might even want to compare week to week, depending on if your Monday and Tuesday traffic is drastically different. Holidays, you really have to watch out for. Especially when it's a holiday not in your country, because then you don't know that's happening. And suddenly there's no traffic. You go, why is there no traffic today? And with the matplotlib stuff, you can say plot this, and then just say, oh, and plot this. And by default, within the iPython notebook, if you put them into that same code chunk, they'll get plotted on the same axes. And we can say, hey, plot the May 7th data using red dots, and label it May 7th, and the May 8th data with blue dots on May 8th. And we have number of rows returned. Please put a legend on it. And sure enough, we can see that there are two different linearizations. The May 8th data takes a little less time for the number of rows returned. And as you can see, it takes a lot less time at the top end, which was a really nice result for us. And for comparison, I didn't change very much about how estimates were rendered. So we can look at the estimate data for the same time frame. So we still have our May 7th after 9 a.m. and May 8th after 9 a.m. We can just filter that down to just estimates and plot that. And we see that at the low end, they really cluster together. They look like they're about the same. At the top end, there's some differentiation, but we get a lot of invoice requests, more than estimates, and it's possible that the invoice requests were actually affecting everything else in the system. So it's kind of neat to see that. But let's be sure. The next week, I deployed the same kind of change to estimates to see if that would have the same effect. And after going through the whole song and dance again for May 14th and May 15th at 9 a.m., we can see that, yes, in fact, it got similarly fast in exactly the same way that we expected. So getting that kind of data is really satisfying as a programmer to say, yes, this week of code that I wrote with meta classes actually made things better. It wasn't a waste. And it's good to be able to go to your stakeholders, to your manager, to the CEO of your company, and say, hey, thank you for letting me spend the time to do this. Here is the actual impact on our customers. They actually spend, we spend a little bit less on server load at the low end for the large number of requests that don't take very long, but are now a little bit faster. And at the top end, there are now customers who used to be waiting, 20 seconds for the response, and now they're only waiting 10. That's a really big difference in user experience. So the other neat thing that I remember asking Wes about, I think it was possibly a year and a half ago, or maybe just earlier in March at PyCon, was about doing these time series analyses using Pandas, where I've got multiple data points per second. It's not like a stock market where you've just got opening and closing or first of the month data. I've got thousands of requests per second, and I want to try to aggregate them in a certain way. And that's what got me doing the other presentation where I did everything in pure Python, because it's actually really easy to do that kind of MapReduce thing where you take requests, you group them together, and you do some kind of aggregation on it. But it turns out that Pandas, especially in Pandas 0.8, can actually do that, and does it, yes, a lot faster than plain Python. So we can load up the May 7th data again. And just to show a bit of data, I'm just going to show the first 10 minutes here. So again, I select the index and index 0 plus 10 minutes. And we're going to call the resample method. Resample has a whole bunch of different ways it can do its resampling to get different intervals. Things like first of the month or first business day of the month, by quarters, by anything like that. And capital T is probably one of the more useful ones for this kind of analysis. It gives us per minute data. And so we can see that, in fact, instead of having these many, many, many data points per second, it's 4 a.m. UTC, 4:01, 4:02, 4:03, and we're getting a NumPy median response. So you can just pass in a callable for how do you want me to aggregate. It'll just get a list of things and be told to do that. Data frames also have a .plot method. So you can pass in something like how equals median and get this nice view of the median response time over the entire day. And you can also pass in other callables like NumPy percentile. It's funny, Michael Featherstock was talking about being able to compose these functions. The NumPy percentile function is not one of them, because the thing that you normally want to pass in as a variable is the first argument, not the second one. So you can't use functional as partial. You have to say NumPy percentile, lambda, all that. But you can very easily get this 25th percentile, 50th percentile, 75th percentile response times. Percentile response times are generally a lot more useful than averages. They keep the outliers way out. You'll want to know those outliers so that you can figure out what the heck happened. But then even the 99th percentile is a much better gauge of how your customers are going to see things, except for those few that just get the horrible result. And the neat thing with this is I can restart this iPython kernel. So now there's a Python interpreter that doesn't know anything, and say, run everything, and it's going to load up an entire day's worth of data and do the resampling and plot the graphs. 1.8 million rows worth of data just crunched like that on my laptop. And we're done. You can have these notebooks. They get saved in JSON format. You can share them with your friends. And it's neat to be able to go back and see what were you doing. As you can see, I'm doing slides in it. You can interleave code and text, markdown, all of that. It's wonderful. So you need 0mq for that. Free type, I think, was to get matplotlib installed. And if you want HDF5 support, you'll also want to install HDF5, which is horrible to install on CentOS 5.5, but not so bad on a Mac. Debian and Ubuntu, there are a few more packages. You might need the C compiler. And then the list of Python packages. iPython, this is web server log analysis. In doing invoicing, people put in clients, create invoices, ship those invoices off. So the kinds of things that we have web requests for are things like give me invoices. And we'll have some examples of that. I've got some actual server logs in here. Fernando mentioned that I should really say, if I'm going to talk about Pandas, that I should mention that Wes McKinney has this book out, Python for Data Analysis, because he's the guy who did Pandas, and it's a really nice book, so you might want to go read it. So, log analysis with Pandas. Pandas, in case you didn't know, is an open source BSD licensed library providing high performance, easy to use data structures and data analysis tools for the Python programming language, straight from the website. Installing it is not the most trivial thing, but it's not that bad. You do need you don't need 0mq for that. You need 0mq for the notebook. The iPython notebook is an awesome tool for interactively working on your code, trying to figure out.
Just big thank you to Fernando Perez.
Oh yes, big thank you to Fernando. Yes, for iPython. And the notebook is really nice.
So I'm very pleased to introduce Taavi. When Taavi's not busily co-organizing PyCon Canadas, he is a defect poacher and futurist at FreshBooks, and he's going to talk to you today about log analysis with Pandas.
Hello. So, log analysis with Pandas. I work at FreshBooks. We do cloud accounting, formerly online invoicing. Really, it's the same thing, but different name. And so we do a lot of web stuff. So the kind of log analysis, we'll then use PyZMQ and Tornado to get the notebook running. And then you'll need NumPy and Matplotlib and Pandas to do the same kinds of things I'm doing here. If you want HDF5 support, you'll also need Python and NumExpert and tables. To run it up, you just go iPython notebook, pylab inline. Pylab says, please import the MATLAB-like functions for just, say, plot. And it imports all of those things into your built-ins. And inline, because we don't want it popping up extra windows. It can be as simple as hello world. And you can go in here and say hello world, PyCon.